going to then take the atoms and form bonds and go up the chain of events to make the molecule. And that's what made me realize, take a toy example, literally toy example, take a Lego object, which is broken up of Lego blocks. So you could do exactly the same thing. In this case, the Lego blocks are naturally the smallest. They're the atoms in the actual composite Lego architecture. But then if you maybe take, a couple of blocks and put them together in a certain way, maybe they're offset in some way. That offset is on the memory. You can use that offset again with only a penalty of 1, and you can then make a square, triangle, and keep going. And you remember those motifs on the chain, so you can then leap from the start with all the Lego blocks or atoms just laid out in front of you and say, right, I'll take you, connect, and do the least amount of work. So it's really like the smallest steps you can take on the graph to make the object. And so for molecules, it came relatively intuitively. And then we started to apply it to language. We've even started to apply it to mathematical theorems. I'm so well out of my depth, but it looks like you can take minimum set of axioms and then start to build up kind of mathematical architectures in the same way. And then the shortest path to get there is something interesting that I don't yet understand.
So what's the computational complexity of figuring out the shortest path with molecules, with language, with mathematical theorems? It seems like once you have the fully constructed Lego castle, or whatever your favorite Lego world is, figuring out how to get there from the basic building blocks is that a hard problem? It's a hard problem.
It's a hard problem, but actually, if you look at it, so the best way to look at it, let's take a molecule. So if the molecule has 13 bonds, first of all, take 13 copies of the molecule and just cut all the bonds. So cut 12 bonds, and then you just put them in order.
Yeah.
And then that's how it works. So you keep looking for symmetry and or copies, so you can then shorten it as you go down, and that becomes combinatorially quite hard. For some natural product molecules, it becomes very hard. It's not impossible, but we're looking at the bounds on that at the moment. But as the object gets bigger, it becomes really hard. But that's the bad news. But the good news is there are shortcuts. And we might even be able to physically measure the complexity without computationally calculating it, which is kind of insane.
Wait, how would you do that?
Well, in the case of molecule, so if you shine light on a molecule, let's take it infrared, the molecule has, each of the bonds absorbs the infrared differently in what we call the fingerprint region. And so it's a bit like, and because it's quantized as well, you have all these discrete kind of absorbances. And my intuition after we realized we could cut molecules up in mass spec, that was the first go at this. We did it with using infrared, and the infrared gave us an even better correlation assembly index. And we used another technique as well, in addition to infrared, called NMR, nuclear magnetic resonance, which tells you about the number of different magnetic environments in a molecule. And that also worked out. So we have 3 techniques, which each of them independently gives us the same or tending towards the same assembly index for a molecule that we can calculate mathematically.
Okay, so these are all methods of mass spectrometry, mass spec. You scan a molecule, it gives you data in the form of a mass spectrum, and you're saying that the data correlates to the assembly index.
Yeah.
So how generalizable is that shortcut? First of all, to chemistry. And second of all, beyond that. Because that seems like a nice hack, and you're extremely knowledgeable about various aspects of chemistry, so you can say, okay, it kind of correlates. But, the whole idea behind assembly theory paper, and perhaps why it's so controversial, is that it reaches bigger. It reaches for the bigger general theory of objects in the universe.
Yeah, I'd say so. I'd agree. So I've started assembly theory of emoticons with my lab, believe it or not. So we take emojis, pixelate them, and work out the assembly index for the emoji, and then work out how many emojis you can make on the path of emoji. So there's the uber emoji from which all other emojis emerge, and then you can then take a photograph, and by looking at the shortest path by reproducing the pixels to make the image you want, you can measure that. So then you start to be able to take spatial data. Now there's some problems there. What is then the definition of the object? How many pixels? How do you break it down? And so we're just learning all this right now.
So how do you compute how would you begin to compute the assembly index of a graphical, like a set of pixels on a 2D plane?
First of all, determine the resolution. So then, what is your XY? And what the number on the X and Y plane? And then look at the surface area. And then you take all your emojis and make sure they're all looked at the same resolution. Yeah. And then we would basically then do exactly the same thing we would do for cutting the bonds. You'd cut bits out of the emoji and look at you'd have a bag of pixels. So and you would then add those pixels together to make the overall emoji.
Wait a minute, but like, first of all, not every pixel's. I mean, this is at the core sort of machine learning and computer vision. Not every pixel is that important, and there's like macro features, there's micro features, and all that kind of stuff.
Exactly.
The eyes appear in a lot of them. The smile appears in a lot of them.
So in the same way in chemistry, we assume the bond is fundamental. What we do in here is we assume the resolution at the scale at which we do it is fundamental. And we're just working that out. And that you're right, that will change, right? Because as you take your lens out a bit, it will change dramatically. But it's just a new way of looking at not just compression, what we do right now in computer science and data. One big kind of misunderstanding is assembly theory is telling you about how compressed the object is. That's not right. It's how much information is required on a chain of events. Because the nice thing is when you do compression in computer science, it's worth wondering. You assume you have instantaneous access to all the information in the memory. In assembly theory, you say, no, you don't get access to that memory until you've done the work. And then you don't access that memory, you can have access, but not the next one. And this is how in assembly theory we talk about the four universes: the assembly universe, the assembly possible, and the assembly contingent, and then the assembly observed. And they're all cells in the assembly theory universe. Yep. So the assembly universe is like anything goes. It's just combinatorial kind of explosion in everything.
So that's the biggest one?
That's the biggest one. It's massive.
Assembly universe, assembly possible, assembly contingent, assembly observed.
Yeah.
And on the y-axis is assembly steps in time.
Yeah.
And, on the x-axis, as the thing expands through time, more and more unique objects appear.
So assembly universe, everything goes.
Yep.
Assembly possible, laws of physics come in this case in chemistry, bonds. Mm-hmm. In assembly, so that means...
Those are actually constraints, I guess?
Yes, and they're the only constraints. They're the constraints at the base. So the way to look at it is you've got all your atoms, they're quantized, you can just bung them together. So then you can become a kind of... So in computer science speak, I suppose, the assembly universe is just like no laws of physics. Things can fly through mountains beyond the speed of light. In the assembly possible, you have to apply the laws of physics, but you can get access to all the motifs instantaneously with no effort. So that means you could make anything. Then the assembly contingent says, no, you can't have access to the highly assembled object in the future until you've done the work in the past on the causal chain. And that's a really interesting shift where you go from assembly possible to assembly contingent. That is really the key thing in assembly theory that says you cannot just have instantaneous access to all those memories. You have to have done the work somehow. The universe has to have somehow built a system that allows you to select that path rather than other paths. And then the final thing, the assembly observed, is basically saying, oh, these are the things we actually see. We can go backwards now and understand that they have been created by this causal process.
Wait a minute. So when you say the universe has to construct the system that does the work, that's like the environment that allows for like selection?
Yeah.
So that's the thing that does the selection.
You could think about it in terms of a non-linear constructor versus a selection, a ribosome, Tesla, a plant assembling Teslas. The difference between the assembly universe in Tesla land and the Tesla factory is everyone says, no, Teslas are just easy. They just spring out. You know how to make them all. The Tesla factory, you have to put things in sequence, and out comes a Tesla.
So you're talking about the factory?
Yes, this is really nice. Super important point is that when I talk about the universe having a memory or there's some magic, it's not that. It's that tells you that there must be a process encoded somewhere in physical reality, be it a cell, a Tesla factory, or something else that is making that object. I'm not saying there's some kind of woo-woo memory in the universe, morphic resonance or something. I'm saying that there is an actual causal process that is being directed and trained in some way. So it's not kind of just making everything.
Yeah, but Lee, what's the factory that made the factory? So what is the... So first of all, you assume the laws of physics is just sprung to existence. Those are constraints. What makes the factory the environment that does the selection?
This is the question of... Well, it's the first interesting question that I want to answer out of 4. I think the factory emerges in the interplay between the environment and the objects that are being built. And here, I'll have a go at explaining to you the shortest path. Why is the shortest path important? Imagine you've got, I'm going to have to go chemistry for a moment, then abstract it. But imagine you've got a given environment that you have a budget of atoms you're just flinging together.
Yep.
And the objective of those atoms that are being flung together in, say, molecule A, have to make it, they decompose. The molecules decompose over time. So the molecules in this environment, in this magic environment, have to not die, but they do die. They have a half-life. The only way the molecules can get through that environment out the other side is when the environment is hot, go in and out without dying. And there's just an infinite supply of atoms coming, or a large supply. The molecule gets built. If the molecule is able to template itself being built and survives in the environment, will basically reign supreme. Now, let's say that molecule takes 10 steps. Now, and it's using a finite set of atoms, right? Or now let's say another molecule, smart mass molecule, comes in and can survive in that environment and can copy itself, but it only needs 5 steps. In 5 steps, both molecules will be destroyed, but they're creating themselves faster they can be destroyed. You can see that the shortest path reigns supreme. So the shortest path tells us something super interesting about the minimal amount of information required to propagate that motif in time and space. And it's just like a kind of, it seems to be like some kind of conservation law.
So one of the intuitions you have is the propagation of motifs in time will be done by the things that can construct themselves in the shortest path.
Yeah.
So like, you can assume that most of the objects in the universe are built before this.
But yes and no, because there are other things. So in the limit, yes, if you want to tell the difference between things that have required a factory to build them and just random processes. But you can find instances where the shortest path isn't taken for an individual object with individual function. And people go, that means the shortest path isn't right. And then I say, well, I don't know. I think it's right still. Because there are other driving forces. There's not just one molecule. Now you start to consider 2 objects, you have a joint assembly space, and it's compromised between not just making A and B in the shortest path, you want to make A and B in the shortest path, which might mean that A is slightly longer and compromised. When you see slightly more nesting in the construction, when you take a given object, that can look longer, but that's because the overall function is the object is still trying to be efficient.
Yeah.
And this is still very hand-wavy, and maybe have no leg to stand on. But we think we're getting somewhere with that.
And there's probably some parallelization.
Yeah.
Right? So this is not sequential. The building is... Yeah, I guess.
No, you're right.
When you're talking about complex objects, you don't have to work sequentially. You can work in parallel. You can get
to it. The thing we're working on right now is how to understand these parallel processes. Now there's a new thing we've introduced called assembly depth. And assembly depth can be lower than the assembly index for a molecule when they're cooperating together. Actually, this parallel processing is going on. And my team have been working this out in the last few weeks because we're looking at what compromises does nature need to make when it's making molecules in the cell. And I wonder if, I'm maybe like, well, I'm always looking out of my competence. But in economics, I'm just wondering if you could apply this in economic process. It seems like capitalism is very good at finding the shortest path. Every time. And there are ludicrous things that happen because actually the cost function has been minimized. And so I keep seeing parallels everywhere where they're complex nested systems, where you give it enough time and you introduce a bit of heterogeneity, the system readjusts and finds a new shortest path. But the shortest path isn't fixed on just one molecule now, it's in the actual existence of the object over time. And that object could be a city, it could be a cell, it could be a factory, but I think we're going way beyond molecules, and my competence probably should go back to molecules. But hey.
All right, before we get too far, let's talk about the assembly equation. Okay, how should we do this? Now, let me just even read that part of the paper. We define assembly as the total amount of selection necessary to produce an ensemble of observed objects, quantified using equation 1. The equation basically has A on one side, which is the assembly of the ensemble, and then a sum from 1 to n, where n is the total number of unique objects. And then there is a few variables in there that include the assembly index, the copy number, which we'll talk about. That's an interesting, I don't remember you talking about that. That's an interesting addition, and I think a powerful one. It has to do with that you can create pretty complex objects randomly. And in order to know that they're not random, that there's a factory involved, you need to see a bunch of them. That's the intuition there. It's an interesting intuition. And then some normalization. What else is it? And
in -1, just to make sure that more than one object. One object could be a one-off and random.
Yep.
And then you have more than one identical object. That's interesting.
When there's two of a thing.
Two of the thing is super important, especially if the assembly index is high.
So we could say several questions here. One, let's talk about selection. What is this term selection? What is this term evolution that we're referring to? Which aspect of Darwinian evolution are we referring to that's interesting here?
So this is probably what, the paper, we should talk about the paper for a second. The paper what it did is it kind of annoyed, we didn't know it. I mean, it got attention, and obviously the angry people were annoyed.
There's angry people in the world. That's good.
So what happened is the evolutionary biologists got angry. We were not expecting that because we thought evolutionary biology would be cool. I knew that some, not many, computational complexity people would get angry because I've kind of been poking them, and maybe I deserved it. But I was trying to poke them in a productive way. And then the physicists kind of got grumpy because the initial conditions tell everything. The prebiotic chemist got slightly grumpy because there's not enough chemistry in there. And then finally, when the creationists said it wasn't creationist enough, I was like, no, I've done my job.
What you say in the physics, they say, because you're basically saying that physics is not enough to tell the story of how biology emerges.
I think so. Classic.
And then they said a few physics is the beginning and the end of the story.
Yeah. So what happened is the reason why people put the phone down on the call, the paper, if you view reading the paper like a phone call, they got to the abstract.
Yep.
And in the abstract,
first sentence is pretty.
The first two sentences caused everybody.
Scientists have grappled with reconciling biological evolution with the immutable laws of the universe defined by physics.
True, right? There's nothing wrong with that statement. Totally true.
Yeah. These laws underpin life's origin, evolution, and the development of human culture and technology, yet they do not predict the emergence of these phenomena. Wow. First of all, we should say the title of the paper. This paper was accepted and published in Nature. The title is Assembly Theory Explains and Quantifies Selection and Evolution. Very humble title. And the entirety of the paper, I think, presents interesting ideas, but reaches high.
I would do it all again. this paper was actually on the preprint server for over a year.
You regret nothing.
Yeah, I think, I don't regret anything.
You and Frank Sinatra did it your way.
What I love about being a scientist is kind of sometimes because I'm a bit dim, I'm like, and I don't understand what people are telling me. I want to get to the point. This paper says, hey, laws of physics are really cool. The universe is great, but they don't really, it's not intuitive that you just run the standard model and get life out. I think most physicists might go, yeah, there's this, it's not just, we can't just go back and say that's what happened, because physics can't explain the origin of life yet. Doesn't mean it won't or can't. Okay, just to be clear, sorry, intelligent designers, we are going to get there. Second point, we say that evolution works, but we don't know how evolution got going. So biological evolution and biological selection. So for me, this seems like a simple continuum. So when I mentioned selection and evolution in the title, I think, and in the abstract, we should have maybe prefaced that and said non-biological selection and non-biological evolution.
Sure.
And then that might have made it even more crystal clear. But I didn't think that biology, evolutionary biology, should be so bold to claim ownership of selection and evolution. And secondly, a lot of evolutionary biologists seem to dismiss the origin of life questions, just say it's obvious. And that causes a real problem scientifically, because when the physicists are like, we own the universe is good, we explain all of it, look at us, and the biologists say we can explain biology, and the poor chemist in the middle going, but hang on. Mm-hmm. And this paper kind of says, hey, there is an interesting disconnect between physics and biology, and that's at the point at which memories get made in chemistry through bonds. And hey, let's look at this close and see if we can quantify it. So yeah, I mean, I never expected the paper to kind of get that much interest, and still, I mean, it's only been published just over a month ago now.
So just to linger on the selection, what is the broader sense of what selection means?
Yeah, that's really good for selection. So I think for selection you need. So this is where for me the concept of an object is something that can persist in time and not die, but basically can be broken up. Mm-hmm. So if I was going to kind of bolster the definition of an object, so if something can form and persist for a long period of time under and exist in an environment that could destroy other, and I'm going to use anthropomorphic terms, I apologize, but weaker objects or less robust, then the environment could have selected that. So good chemistry examples, if you took some carbon and you made a chain of carbon atoms, whereas if you took some carbon, nitrogen and oxygen and made chains from those, you start to get different reactions and rearrangements. So a chain of carbon atoms might be more resistant to falling apart under acidic or basic conditions versus another set of molecules. So it survives in that environment. So the acid pond, the resistant molecule can get through, and then that molecule goes into another environment. So that environment now maybe being an acid pond is a basic pond, or maybe it's an oxidizing pond. And so if you've got carbon and it goes in an oxidizing pond, maybe the carbon starts to oxidize and break apart. So you go through all these kind of obstacle courses, if you like, given by reality. So selection is the ability happens when an object survives in an environment for some time, but, and this is the thing that's super subtle, the object has to be continually being destroyed and made by process. So it's not just about the process, the object now, it's about the process and time that makes it. Because a rock could just stand on the mountainside for 4 billion years and nothing happened to it. And that's not necessarily really advanced selection. So for selection to get really interesting, you need to have a turnover in time. Mm-hmm. You need to be continually creating objects, producing them, what we call discovery time. So there's a discovery time for an object. When that object is discovered, if it's, say, a molecule that can then act on itself, or the chain of events that caused itself to bolster its formation, then you go from discovery time to production time, and suddenly you have more of it in the universe. So it could be a self-replicating molecule. And the interaction of the molecule in the environment, in the warm little pond or in the sea or wherever, in the bubble, could then start to build a proto-factory, the environment. So really, to answer your question, what the factory is the environment, but it's not very autonomous. It's not very redundant. There's lots of things that could go wrong. So once you get high enough up the hierarchy of networks of interactions, something needs to happen that needs to be compressed into a smaller volume and made resistant and robust. Because in biology, selection and evolution is robust. That you have error correction built in. You have really, there's good ways of basically making sure propagation goes on. So really the difference between inorganic, abiotic selection and evolution and stuff in biology is robustness, the ability to kind of propagate over the ability to survive in lots of different environments. Whereas our poor little inorganic soul molecule, whatever, just dies in lots of different environments. So there's something super special that happens from the inorganic molecule in the environment that kills it to where you've got evolution and cells can survive everywhere.
How special is that? How do you know those kinds of evolution factors aren't everywhere in the universe?
I don't, and I'm excited because I think selection isn't special at all. I think what is special is the history of the environments on Earth that gave rise to the first cell that now has taken all those environments and is now more autonomous. And I would like to think that, this paper could be very wrong. But I don't think it's very wrong. I mean, it's certainly wrong, but it's less wrong than some other ideas, I know, right? And if this inspires us to go and look for selection in the universe, because we now have an equation where we can look for selection going on and say, oh, that's interesting. We seem to have a process that's giving us high copy number objects that also are highly complex, but that doesn't look like life as we know it. And we use that and say, oh, there's a hydrothermal vent. Oh, there's a process going on, there's molecular networks, because the assembly equation is not only meant to identify at the higher end advanced selection, what you get, I would call it in biology, super advanced selection. And even, you could use the assembly equation to look for technology and God forbid we could talk about consciousness and abstraction, but let's keep it primitive, molecules and biology. So I think the real power of the assembly equation is to say how much selection is going on in this space. And there's a really simple thought experiment I could do. If you have a little petri dish, and on that petri dish you put some simple food, so the assembly index of all the sugars and everything is quite low. So there, and you put a single cell of E. coli cell, and then you say, I'm gonna measure the assembly in this amount of assembly in the box. It's quite low, but the rate of change of assembly, dA dt, will go sigmoidal as it eats all the food, and the number of coli cells will replicate because they take all the food, they can copy themselves. The assembly index of all the molecules goes up, 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 and up until the food is exhausted in the box. So now the E. coli's stop. Die is probably a strong word. They stop respiring because all the food is gone, but suddenly the amount of assembly in the box has gone up gigantically because of that one E. coli factory has just eaten through, milled lots of other E. coli factories, run out of food and stopped. And so that, looking at that, so in the initial box, although the amount of assembly was really small, it was able to replicate and use all the food and go up. And that's what we're trying to do in the lab, actually, is kind of make those kind of experiments and see if we can spot the emergence of molecular networks that are producing complexity as we feed in raw materials and we feed a challenge, an environment. We try and kill the molecules. And really, that's the main kind of idea for the entire paper.
Yeah, and see if you can measure the changes in the assembly index throughout the whole system.
Yeah.
Okay, what about if I show up to a new planet, we go to Mars or some other planet from a different solar system, and how do we use assembly index there to discover alien life?
In very simply, actually, let's say we'll go to Mars with a mass spectrometer with a sufficiently high resolution. So what you have to be able to do. So a good thing about mass spec is that you can select the molecule from the mass, and then if it's high enough resolution, you can be more and more sure that you're just seeing identical copies. You can count them, and then you fragment them and you count the number of fragments and look at the molecular weight. And the higher the molecular weight and the higher the number of the fragments, the higher the assembly index. So if you go to Mars and you take a mass spec or high enough resolution, and you can find molecules, I'll give a guide on Earth. If you could find molecules, say, greater than 350 molecular weight or more than 15 fragments, you have found artifacts that can only be produced, at least on Earth, by life. Now, you would say, oh, well, maybe the geological process. I would argue very vehemently that that is not the case. But we can say, look, if you don't like the cutoff on Earth, go up higher, 30, 100, right? Because there's going to be a point where you find a molecule with so many different parts, the chances of you getting a molecule that has 100 different parts and finding a million identical copies, that's just impossible. That could never happen in an infinite set of universes.
Can you just linger on this copy number thing? A million different copies. What do you mean by copies, and why is the number of copies important?
Yeah, that was so interesting, and that I always understood the copy number is really important, but I never explained it properly for ages. And I kept having this. It goes back to this. If I give you a really complicated molecule, and I say it's complicated, you could say, hey, that's really complicated, but is it just really random? And so I realized that ultimate randomness and ultimate complexity are indistinguishable until you can see a structure in the randomness. So you can see copies.
So copies implies structure.
Yeah. The factory.
I mean, there's a deep, profound thing in there. Because if you just have a random process, you're going to get a lot of complex, beautiful, sophisticated things.
Mm-hmm.
What makes them complex in the way we think life is complex, or something like a factory that's operating under a selection process, is there should be copies. Is there like some looseness about copies? Like, what does it mean for two objects to be equal?
It's all to do with the telescope or the microscope you're using. And so at the maximum resolution, so in the nice thing about chemists is they have this concept of the molecule, and they're all familiar with a molecule. And molecules you can hold, on your hand, and lots of them, identical copies. A molecule is actually a super important thing in chemistry to say, look, you can have a mole of a molecule, so an Avogadro's number of molecules, and they're identical. What does that mean? That means that the molecular composition, the bonding and so on, the configuration is indistinguishable. You can hold them together, you can overlay them. So the way to do it is if I say, here's a bag of 10 identical molecules. Let's prove they're identical. You pick one out of the bag, and you basically observe it using some technique, and then you take it away, and then you take another one out. If you observe it using technique, you see no differences. They're identical. Really interesting, right? Because if you take, say, two molecules can be in different vibrational and rotational states. They're moving all the time. So in this respect, identical molecules have identical bonding. In this case, we don't even talk about chirality, because we don't have a chirality detector. So two identical molecules in one conception assembly theory basically considers both hands as being the same. But of course, they're not. They're different. As soon as you have a chiral distinguisher detect the left and the right hand, they become different. And so it's to do with the detection system that you have and the resolution.
So I wonder if there's an art and science to which detection system is used when you show up to a new planet.
Yeah.
So like you're talking about chemistry a lot today. We have kind of standardized detection systems, right, of how to compare molecules. So, when you start to talk about emojis and language and mathematical theorems and I don't know, more sophisticated things at a different scale, at a smaller scale the molecules, at a larger scale the molecules, like what detection, like if we look at the difference between you and me, Lex and Lee, are we the same? Are we different?
Sure. I mean, of course we're different close up, But if you zoom out a little bit, it
Yes.
will morphologically look the same.
Yeah.
Not height, characteristics, hair length, stuff like that.
Well, also like the species and
Yeah.
and also there's a sense why we're both from Earth.
Yeah, I agree. I mean, this is the power of assembly theory in that regard. That if everything, so the way to look at it, if you have a box of objects, if they're all indistinguishable, then using your technique, what you then do is you then look at the assembly index. Now, if the assembly index of them is really low, right, and they're all indistinguishable, then it's telling you that you have to go to another resolution. So that would be, it's kind of a sliding scale. It's kind of nice.
So those two kind of are in tension with each other.
Yeah.
The number of copies and the assembly index.
Yeah.
That's really, really interesting. So you show up to a new planet, you'll be doing what?
I would do mass spec. I would bring
on a sample of what? Like, first of all, like how big of a scoop do you take? Did you just take a scoop? Like what? Like, so we're looking for primitive life.
I would look. Yeah. So if you're just going to Mars or Titan or Enceladus or somewhere, so a number of ways of doing it. So you could take a large scoop, or you could go for the atmosphere and detect stuff. So and you could make a life meter, right? So one of Sarah's colleagues at ASU, Paul Davies, keeps calling it a life meter, which is quite a nice idea because you think about it. If you've got a living system that's producing these highly complex molecules, and they drift away, and they're in a highly demanding environment, they could be burnt, right? So they could just be falling apart. So you want to sniff a little bit of complexity and say warmer. Oh, we found life. We found the alien. We found the alien Elon Musk smoking a joint in the bottom of the cave on Mars, or Elon himself, whatever, right? You say, okay, found it. So what you can do is the mass spectrometer. You could just look for things in the gas phase, or you go on the surface, drill down, because you want to find molecules that are where you've either got to find the source living system, because the problem with just looking for complexity is it gets burnt away. So in a harsh environment on say on the surface of Mars, there's a very low probability that you're going to find really complex molecules because of all the radiation and so on. If you drill down a little bit, you could drill down a bit into soil that's billions of years old. Then I would put in some solvent, water, alcohol or something, or take a scoop, make it volatile, put it into the mass spectrometer and just try and detect high complexity, high abundant molecules. And if you get them, hey presto, you can have evidence of life. Wouldn't that then be great if you could say, okay, we've found evidence of life. Now we want to keep the life meter, keep searching for more and more complexity until you actually find living cells. You can get those new living cells, and then you could bring them back to Earth, or you could try and sequence them. You could see that they have different DNA and proteins.
Go along the gradient of the life meter.
Exactly.
How would you build a life meter? Let's say we're together, starting
a
new company, launching a life meter.
Mass spectrometer would be the first way of doing it.
No, but that's one of the major components of it. But I'm talking about like, what if it's a device? We got and branding, logo. We got to talk about that. That's later. But what's the input? What's the how do you get to the a metered output?
So I would take a life. So my life meter, our life meter. There you go.
Thank you.
Yeah, you're welcome. Would have both infrared and mass spec. So it would have two ports, so we could shine a light. And so what it would do is you would have a vacuum chamber, and you would have an electrostatic analyzer, and you'd have a monochromator to producing infrared. You'd add the so you'd take a scoop of the sample, put it in the life meter. It would then add a solvent or heat up the sample, so some volatiles come off. The volatiles would then be put into the mass spectrometer, into the electrostatic trap, and you'd weigh the molecules and fragment them. Alternatively, you'd shine infrared light on them, and you'd count the number of bands. But you'd have to, in that case, do some separation, because you want to separate. And so in mass spec, it's really nice and convenient because you can separate electrostatically, but you need to have that.
Can you do it in real time?
Yeah, pretty much. Yeah. So let's go all the way back. So okay, we're really going to get this. The Lex's life meter. Lex and Lee's life meter.
Excellent. Yeah, it's a good ring to it.
All right. So you have a vacuum chamber. You have a little nose. The nose would have a packing material. So you would take the sample, add it onto the nose, hold it like that. So it can be sucked up the nose, and that would be separated using chromatography. And then as each band comes off the nose, we then do mass spec and infrared. And in the case of infrared, count the number of bands. In the case of mass spec, count the number of fragments, weigh it. And then the further up in the molecular weight range for the mass spec, the number of bands will go up and up and up from the dead, interesting, over the threshold. Oh my gosh, Earth life. And then right up to batshit crazy. This is definitely, alien intelligence to make this life, right? You could almost go all the way there, frame an infrared. And it's pretty simple. The thing that is really problematical is that for many years, decades, what people have done, and I can't blame them, is they've been obsessing about small biomarkers that we find on Earth, amino acids, like single amino acids, or evidence of small molecules and these things, and looking for those rather than looking for complexity. The beautiful thing about this is you can look for complexity without Earth chemistry bias or Earth biology bias. So assembly theory is just a way of saying, hey, complexity and abundance is evidence of selection. That's how our universal life meter will work.
Complexity in abundance is evidence of selection. Okay, so let's apply our life meter to Earth. So what, if we were just to apply assembly index measurements to Earth, what kind of stuff are going to get? What's impressive about some of the complexity on Earth?
So we did this a few years ago when I was trying to convince NASA and colleagues that this technique could work. And honestly, it's so funny because everyone's like, no, it ain't going to work. And it was just like, because the chemists were saying, of course there are complicated molecules out there you can detect that just form randomly. I was like, really? That was like, it was a bit like I don't know, someone saying, of course Darwin textbook was just written randomly by some monkeys on a typewriter. For me, it was like, really? And I pushed a lot on the chemists now, and I think most of them are on board, but not totally. I really had some big arguments, but the copy number got there because I think I confused the chemist by saying one off, and then when I made clear about the copy number, I think that made it a little bit easier.
Just to clarify, chemists might say that, of course, out there outside of Earth, there's complex molecules.
Yes.
Okay. And then you're saying, wait a minute, that's like saying, of course, there's aliens out there.
Yeah, exactly that.
Okay.
Exactly.
But you're saying, you clarify that that's actually a very interesting question, and we should be looking for complex molecules of which the copy number is 2 or greater.
Yeah, exactly. So on Earth, coming back to Earth, what we did is we took a whole bunch of samples. We were running prebiotic chemistry experiments in the lab. We took various inorganic minerals and extracted them. Look at the volatile, because there's a special way of treating minerals and polymers in assembly theory, where in our life machine, we're looking at molecules. We don't care about polymers because they're not volatile. You can't hold them. They're not. How can you make, if you can't ascertain that they're identical, then it's very difficult for you to work out if they're undergone selection or they're just a random mess. Same with some minerals, but we can come back to that. So basically what you do, we got a whole load of samples, inorganic ones. We got Scotch whiskey, and also took Ardbeg, which is one of my favorite whiskies, which is very peaty. And another whiskey is like, so the way that in Scotland, in Islay, which is a little island, the whiskey is let to mature in barrels, and it's said that the peat, the complex molecules in the peat might find their way through into the whiskey, and that's what gives it this intense brown color and really complex flavor. It's literally molecular complexity that does that. And so, vodka is the complete opposite. It's just pure, right?
So the better the whiskey, the higher the assembly index. Or the higher the assembly index, the better the whiskey.
That's what I mean. I really love deep, peaty Scottish whiskies. Near my house, there is one of the lowland distilleries called Glengoyne. It's still beautiful whiskey, but not as complex. So for fun, I took some Glengoyne whiskey in our bag and put them into the mass spec and measure the assembly index. I also got E. coli. So the way we do it, take the E. coli, break the cell apart, take it all apart, and also got some beer. And people were ridiculing us, saying, "Oh, beer is evidence of complexity." We kind of he's very vigorous in his disagreement of assembly theory. Was just saying, you don't know what you're doing. Even beer is more complicated than human. We didn't realize is that it's not beer per se. It is taking the yeast extract, breaking the cells, extracting the molecules, and just looking at the profile of the molecules, see if there's anything over the threshold. And we also put in a really complex molecule Taxol. So we took all of these, but also NASA gave us, I think, 5 samples, and they wouldn't tell us what they are. They said, "No, we don't believe you can get this to work." And they really, they gave us some super complex samples, and they gave us 2 fossils, one that was 1 million years old and one was at 10,000 years old, something from Antarctica, seabed. They gave us a Murchison meteorite and a few others. Put them through the system. So we took all the samples, treated them all identically, put them into mass spec, fragmented them, counted, and in this case, implicit in the measurement was you in mass spec you only detect peaks when you've got more than let's say 10,000 identical molecules. So the copy number is already baked in, but wasn't quantified, which is super important there. This is in the first paper because I was like, it's abundant, of course. And when you then took it all out, we found that the biological samples gave you molecules that had an assembly index greater than 15, and all the abiotic samples were less than 15. And then we took the NASA samples and we looked at the ones that were more than 15 and less than 15, and we gave them back to NASA. And they're like, "Oh gosh, yep, dead, living, you got it." And that's what we found on Earth.
That's a success.
Yeah. Oh yeah, resounding success.
Well, can you just go back to the beer and the E. coli? So what's the assembly index on those?
So what you were able to do is like the assembly index we found high assembly index molecules originating from the beer sample and the E. coli sample. So
the yeast on the beer.
I mean, there were. I didn't know which one was higher. We didn't really do any detail there because now we are doing that because one of the things we've done. It's a secret, but I can tell you. I think
No, nobody's listening.
Well, is that we've just mapped the tree of life using assembly theory because everyone said, "Oh, that you can't do it from biology." And what we're able to do is, I think there's 2 ways of doing tree of life. 3 ways actually.
Yeah, what's the tree of life?
So the tree of life is basically tracing back the history of life on Earth, all the different species, going back who evolved from what, and it all goes all the way back to the first kind of life forms, and they branch off, and like you have plant kingdom, the animal kingdom, the fungi kingdom, and different branches all the way up. And the way this was classically done, and I'm no evolutionary biologist, the evolutionary biologists tell me every day, at least 10 times. I want to be one though. I kind of like biology. It's kind of cool. But
yeah, it's very cool.
But basically, what Darwin and Mendeleev and all these people do is they draw pictures, right? And they taxa. They were able to draw pictures and say, "Oh, these look like common classes."
Yeah.
Then
they're artists, really. They're just
But they were able to find out a lot, right? And looking at vertebrates, Cambrian explosion, and all this stuff, and then came the genomic revolution, and suddenly everyone used gene sequencing. And Craig Venter's a good example. I think he's gone around the world in his yacht just picking up samples, looking for new species, where he's just found new species of life just from sequencing. It's amazing. So you have taxonomy, you have sequencing, and then you can also do a little bit of kind of molecular kind of archaeology, like, measure the samples and kind of form some inference. What we did is we were able to fingerprint. So we took a load of random samples from all of biology, and we used mass spectrometry. And what we did now is not just look for individual molecules, but we looked for coexisting molecules where they had to look at their joint assembly space, and where we were able to cut them apart and undergo recursion in the mass spec and infer some relationships, and we were able to recapitulate the tree of life using mass spectroscopy. No sequencing and no drawing.
All right. Can you try to say that again with a little more detail? So recreating, what does it take to recreate the tree of life? What does the reverse engineering process look like here?
So what you do is you take an unknown sample, you bung it into the mass spec, you get because this comes from what you asked, like what you see in E. coli.
Mm-hmm.
And so in E. coli, you don't just see, it's not the most sophisticated cells on Earth make the most sophisticated molecules. It is the coexistence of lots of complex molecules above a threshold.
Mm-hmm.
And so what we realized is you could fingerprint different life forms. So fungi make really complicated molecules. Why? Because they can't move. They have to make everything on site.
Mm-hmm.
Whereas, some animals are like lazy. They can just go eat the fungi. They don't need to make very much. And so what you do is you look at so you take, I don't know, the fingerprint, maybe the top number of high molecular weight molecules you find in the sample, you fragment them to get their assembly indices. And then what you can do is you can infer common origins of molecules. You can do a kind of molecular, when the reverse engineering of the assembly space, you can infer common roots and look at what's called the joint assembly space. Let's translate that into the experiment. Take a sample, bung it in the mass spec, take the top, say, 10 molecules, fragment them, and that gives you one fingerprint. Then you do it for another sample, you get another fingerprint. Now the question is, you say, hey, are these samples the same or different? And that's what we've been able to do. And by basically looking at the assembly space that these molecules create. Without any knowledge of assembly theory, you are unable to do it. With a knowledge of assembly theory, you can reconstruct the tree.
How does knowing if they're the same or different give you the tree?
Let's go to 2 leaves on different branches on the tree, right? What you can do by counting the number of differences, you can estimate how far away their origin was.
Got it.
And that's all we do. And it just works. But when we realized you could even use assembly theory to recapitulate the tree of life with no gene sequencing, we were like, huh.
So this is looking at samples that exist today in the world. What about like things that are no longer exist? I mean, the tree contains information about the past. Some of it is gone.
Yeah, absolutely. I would love to get old fossil samples and apply assembly theory mass spec and see if we can find new forms of life that are no longer amenable to gene sequencing because the DNA is all gone. Because DNA and RNA is quite unstable, but some of the more complex molecules might be there and might give you a hint, something new. Or wouldn't it be great if you find a sample that's worth really persevering and doing the proper extraction to PCR and so on, and then sequence it and then put it together.
So when a thing dies, you can still get some information about its complexity.
Yeah, and it appears that you can do some dating. Now, there are really good techniques. There's radiocarbon dating. There is longer dating, looking at radioactive minerals and so on. And you can also, in bone, you can look at what happens after something dies is you get what's called racemization, where the chirality in the polymers basically changes, and you get decomposition, and the rate of the deviation from the pure enantiomer to the mixture, you can have it gives you a time scale on it, a half-life, so you can date when it died. I want to use assembly theory to see if I can date death and things, and trace the tree of life and also decomposition of molecules.
You think it's possible?
Oh yeah, without a doubt. It may not be better than because I was just at a conference where some brilliant people were looking at isotope enrichment and looking at how life enriches isotopes, and they're really sophisticated stuff that they're doing. But I think there's some fun to be had there because it gives you another dimension of dating. How old is this molecule? In terms of, or more importantly, how long ago was this molecule produced by life? Mm-hmm. The more complex the molecule, the more prospect for decomposition, oxidation, reorganization, loss of chirality, and all that jazz. But what life also does is it enriches. As you get older, the amount of carbon-13 in you goes up. Because of the way the metabolite, because of the way the bonding is in carbon-13, so it has a slightly different bond strength than you. It's called the kinetic isotope effect. So you can literally date how old you are, or when you stop metabolizing. So you could date someone's death, how old they are. I think I'm making this up. This might be right, but I think it's roughly right. The amount of carbon-13 you have in you, you can kind of estimate how old you are.
How old living humans are? Or living
organisms? Like you could say, oh, this person is 10 years old and this person 30 years old because they'll be metabolizing more carbon and they've accumulated it. Yeah. That's the basic idea. It's probably completely wrong timescale.
Signatures of chemistry are fascinating. Yeah. So you've been saying a lot of chemistry examples for assembly theory. What if we zoom out and look at a bigger scale of an object? Like really complex objects, like humans or living organisms that are made up of millions or billions of other organisms. How do you try to apply assembly theory to that?
At the moment, we should be able to do this to morphology in cells. So we're looking at cell surfaces, and really I'm trying to extend further. It's just that we work so hard to get this paper out and people to start discussing the ideas, but it's kind of funny because I think the penny is falling on this. So
what's that even? What's it mean for a penny to be?
No, I mean no, the penny's dropped, right? Because a lot of people are like, it's rubbish. You've insulted me. It's wrong. And then the paper got published on the 4th of October. It had 2.3 million engagements on Twitter, right? And it's been downloaded over a few 100,000 times. And someone actually wrote to me and said, this is an example of really bad writing and what not to do. And I was like, if all of my papers got read this much, because that's the objective, if I have a publishing a paper, I want people to read it, I want to write that badly again.
Yeah. I don't know what's the deep insight here about the negativity in the space. I think it's probably the immune system of the scientific community making sure that there's no bullshit that gets published. And then it can overfire, it can do a lot of damage, it can shut down conversations in a way that's not productive.
And I go back, I'll answer your question about the hierarchy in assembly, but let's go back to the perception. People saying the paper was badly written, of course we could improve it. We can always improve the clarity.
Let's go there before we go to the hierarchy.
Yeah.
It has been criticized quite a bit, the paper. What has been some criticism that you found most powerful, like that you can understand, and can you explain it?
The most exciting criticism came from the evolutionary biologists telling me they thought that origin of life was a solved problem, and I was like, whoa, we're really onto something, because it's clearly not. And when you poke them on that, they just said, no, you don't understand evolution. And I said, no, I don't think you understand that evolution had to occur before biology, and there's a gap. That was really, for me, that misunderstanding, and that did cause an immune response, which was really interesting. The second thing was the fact that physicists were actually really polite, right? Really nice about it. But they just said, we're not really sure about the initial conditions thing, but this is a really big debate that we should certainly get into, because the emergence of life was not encoded in the initial conditions of the universe. And it can't, and I think assembly theory shows why it can't be.
Okay, say that. Sure. If you could say that again.
The origin of the emergence of life was not and cannot, in principle, be encoded in the initial conditions of the universe.
Just to clarify what I mean by life is like what, high assembly index objects?
Yeah. And this goes back to your favorite subject.
What's that?
Time.
Right. So why? What does time have to do with it?
Probably we can come back to it later, but I think it might be if we have time.
Yeah.
But I think that I think I now understand how to explain how lots of people got angry with the assembly paper, but also the ramifications of this is how time is fundamental in the universe, and this notion of combinatorial spaces. And there are so many layers on this, but you have to become I think you have to become an intuitionist mathematician, and you have to abandon Platonic mathematics, and also Platonic mathematics has left physics astray, but there's a lot to unpack there. So we can go to the
Platonic mathematics. Okay, hey, it's okay. The evolutionary biologists criticize because the origin of life is understood and not. It doesn't require an explanation that involves physics.
Yeah,
that's their statement.
Well, I mean, it was. I think they said lots of confusing statements. Basically, I realized the evolutionary biology community that were vocal, and some of them were really rude, really spiteful, and needlessly so, right? Because, look, you know, I didn't. People misunderstand publication as well. Some of the people have said, "How dare this be published in Nature? This is, you know, what a terrible journal." And it really, and I wanted to say to people, look, this is a brand new idea that's not only potentially going to change the way we look at biology, it's going to change the way we look at the universe. And everyone's like saying, "How dare you? How dare you be so grandiose?" I'm like, no, this is not hype. We're not like saying we've invented some, I don't know, we've discovered an alien in a closet somewhere just for hype. We genuinely mean this to genuinely have the impact or ask the question. And the way people jumped on that was a really bad precedent for young people who want to actually do something new, because this makes a bold claim. And the chances are that it's not correct. But what I wanted to do is a couple of things. I wanted to make a bold claim that was precise and testable and correctable, not another woolly information in biology argument, information Turing machine, blah, 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 blah. A concrete series of statements that can be falsified and explored, and either the theory could be destroyed or built upon.
Well, what about the criticism of you're just putting a bunch of sexy names on something that's already obvious?
Yeah, that's really good. So the assembly index of a molecule is not obvious. No one had measured it before. And no one has thought to quantify selection, complexity, and copy number before in such a primitive, quantifiable way. I think the nice thing about this paper is a tribute to all, well, not to all the people that understand that biology does something very interesting. Some people call it negentropy. Some people call it, think about, you know, organizational principles. That lots of people were not shocked by the paper because they'd done it before. A lot of the arguments we got, some people said, "Oh, it's rubbish. Oh, by the way, I had this idea 20 years before." I was like, which one? Is it the rubbish part or the really revolutionary part? So this kind of plucked two strings at once. It plucked there is something interesting that biology does, we can see around this, but we haven't quantified yet. And what this is, the first stab at quantifying that. So the fact that people said this is obvious, but it's also so if it's obvious, why have you not done it?
Sure, but there's a few things to say there. One is, you know, this is in part a philosophical framework, because, you know, it's not like you can apply this generally to any object in the universe. It's very chemistry focused.
Yeah, well, I think you will be able to. We just haven't got there robustly. So we can say, how can we? Let's go up a level. So we go up from level. Let's go up from molecules to cells, because you jump to people, and I jump to emoticons, and both are good, and they will be assemblies.
Let's stick with cells. Yeah.
So if we go from molecules to assemblies. And let's take a cellular assembly. A nice thing about a cell is you can tell the difference between a eukaryote and a prokaryote, right? The organelles are specialized differently. We then look at the cell surface, and the cell surface has different glycosylation patterns, and these cells will stick together. Now let's go up a level in multicellular creatures. You have cellular differentiation. Now, if you think about how embryos develop, you go all the way back. Those cells undergo differentiation in a causal way that's biomechanically a feedback between the genetics and biomechanics. I think we can use assembly theory to apply to tissue types. We can even apply it to different cell disease types. So that's what we're doing next. But we're trying to walk, you know, the thing is, I'm trying a leap ahead. I want to leap ahead to go, well, we apply it to culture. But clearly, you can apply it to memes and culture. And we've also applied assembly theory to CAs, and not as you think.
Cellular automata, by the
Yeah,
way.
yeah. So not just as you think. Different CA rules were invented by different people at different times. And one of my co-workers, very talented chap, basically was like, "Oh, I can realize that different people had different ideas or different rules, and they copied each other and made slightly different different cellular automata rules, and looked at them online." And so he was able to refer an assembly index and copy number of rule whatever doing this thing. But I digress. But it does show you can apply it at a higher scale. So what do we need to do to apply assembly theory to things? We need to agree there's a common set of building blocks. So in a cell, well, in a multicellular creature, you need to look back in time. So there is the initial cell, which the creature is fertilized and then starts to grow. And then there is cell differentiation, and you have to then make that causal chain both on those. So that requires development of the organism in time. Or if you look at the cell surfaces and the cell types, they've got different features on the cell, walls and inside the cell. So we're building up. But obviously, I want a leap to things like emoticons, language, mathematical theorems.
But that's a very large number of steps to get from a molecule to the human brain.
Yeah, and I think they are related, but in hierarchies of emergence, right? So you shouldn't compare them. I mean, the assembly index of a human brain, what does that even mean? Well, maybe we can look at the morphology of the human brain, say all human brains have these number of features in common. If they have those and then let's look at a brain in a whale or a dolphin or a chimpanzee or a bird. Say, okay, let's look at the assembly indices, number of features in these. And now the copy number is just a number of how many birds are there, how many chimpanzees are there, how many humans are there.
But then you have to discover for that the features that you would be looking for.
Yeah, and that means you need to have some idea of the anatomy.
Is there an automated way to discover features?
I guess so. I mean, and I think this is a good way to apply machine learning and image recognition, just to basically characterize things.
So apply compression to it to see what emerges, and then use the features used as part of the compression as the measurement of as the thing that is searched for when you're measuring assembly index and copy number.
And the compression has to be, remember, the assembly universe, which is you have to go from assembly possible to assembly contingent, and that jump from because assembly possible, all possible brains, all possible features all the time. But we know that on the tree of life and also on the lineage of life, going back to Luca, the human brain just didn't spring into existence yesterday. It is a long lineage of brains going all the way back. And so if we could do assembly theory to understand the development, not just in evolutionary history, but in biological development, as you grow, we are going to learn something more.
What would be amazing is if you can use assembly theory, this framework, to show the increase in the assembly index associated with, I don't know, cultures or pieces of text like language or images and so on, and illustrate without knowing the data ahead of time, just kind of like you did with NASA, that you're able to demonstrate that it applies in those other contexts. I mean, and that, probably wouldn't at first, and you have to evolve the theory somehow. You have to change it, you have to expand it,
I think so.
But like that, I guess this is, as a paper, a first step in saying, okay, can we create a general framework for measuring complexity of objects, for measuring life, the complexity of living organisms?
Yeah.
That's what this is reaching for.
That is the first step, and also to say, look, we have a way of quantifying selection and evolution in a fairly not mundane, but a fairly mechanical way.
Yeah.
Because before now it wasn't the ground truth for it was very subjective. Whereas here we're talking about clean observables, and there's going to be layers on that. I mean, with collaborators right now, we already think we can do assembly theory on language, and not only that, wouldn't it be great if we can figure out how under pressure language is going to evolve and be more efficient? because you're going to want to transmit things. And again, it's not just about compression. It is about understanding how you can make the most of the architecture you've already built. And I think this is something beautiful that evolution does. We're reusing those architectures. We can't just abandon our evolutionary history. And if you don't want to abandon your evolutionary history, and you know that evolution has been happening, then assembly theory works. And I think that's a key comment I want to make, is that assembly theory is great for understanding when evolution has been used. The next jump is when we go to technology, because of course, if you take the M3 processor, I haven't bought one yet, I can't justify it, but I want to at some point. The M3 processor arguably there's quite a lot of features, a quite large number. The M2 came before it, then the M1, all the way back. You can apply assembly theory to microprocessor architecture. It doesn't take a huge leap to see that.
I'm a Linux guy, by the way, so your examples go way over my
Yeah,
head.
well, whatever.
Is that like a fruit company of some sort? I don't even know. Yeah, there's a lot of interesting stuff to ask about language. Like you could look at, how would that work? You could look at GPT-1, GPT-2, GPT-3, 3, 5, 4, and try to analyze the kind of language it produces. I mean, that's almost trying to look at assembly index of intelligent systems.
Yeah, I mean, I think the thing about large language models, and this is a whole hobby horse I have at the moment, is that obviously they're all about the evidence of evolution in the large language model comes from all the people that produced all the language, and that's really interesting, and all the corrections in the Mechanical Turk, right?
Sure.
And so
but that's part of the history, part of the memory of the system.
Exactly. So so it would be really interesting to basically use an assembly-based approach to making language in a hierarchy, right? I think my guess is that we might be able to build a new type of large language model that uses assembly theory, that it has more understanding of the past and how things were created. Basically, the thing with LLMs is they're like everything, everywhere, all at once, splat, and make the user happy. So there's not much intelligence in the model. The model is how the human interacts with the model. But wouldn't it be great if we could understand how to embed more intelligence in the system?
What do you mean by intelligence there? Like, you seem to associate intelligence with history.
Yeah, well,
memory.
I think selection produces intelligence.
You're almost implying that selection is intelligence. No.
Yeah, kind of. I would go out on a limb and say that, but I think it's a little bit more. Human beings have the ability to abstract, and they can break beyond selection, and this is what like Darwinian selection, because a human being doesn't have to basically do trial and error.
Yeah.
Like they can think about it and say, "Oh, that's a bad idea. Won't do that," and then technologies and so on.
So we escaped Darwinian evolution, and now we're on to some other kind of evolution, I guess.
Yeah.
Higher level evolution.
And we'll assembly theory will measure that as well, right? Because it's all a lineage.
Okay, another piece of criticism, or by way of question, is how is assembly theory, or maybe assembly index, different from Kolmogorov complexity? So for people who don't know, Kolmogorov complexity of an object is the length of a shortest computer program that produces the object as output.
Yeah, there seems to be a disconnect between the computational process. So a Kolmogorov measure requires a Turing machine, requires a computer, and that's one thing. And the other thing is, assembly theory is supposed to trace the process by which life evolution emerged. Right? There's a main thing there. There are lots of other layers. So Kolmogorov complexity, you can approximate Kolmogorov complexity, but it's not really telling you very much about the actual. It's really telling you about like your data set, compression of your data set.
Sure.
And so that doesn't really help you identify the turtle, in this case, is the computer. And so what assembly theory does is, I'm going to say, it's a trigger warning for anyone listening who loves complexity theory. I think that we're going to show that AIT is a very important subset of assembly theory, because here's what happens. That I think that assembly theory allows us to build, understand when selection's occurring. Selection produces factories and things. Factories in the end produce computers, and you can go then algorithm with looking at life through this kind of information theory is it doesn't take into account causation. The main difference between assembly theory and all these complexity measures is there's no causal chain.
Yeah.
And I think that's the main.
That's the causal chain is at the core of assembly theory.
Exactly. And if you've got all your data in the computer memory, all the data is the same. You can access it in the same way. You don't care. You just compress it, and you either look at the program runtime or the shortest program. And that, for me, it is absolutely not capturing what its selection does.
But assembly theory looks at objects. It doesn't have information about the object history. It's going to try to infer that history by looking for the shortest history, right? Like
So,
the object doesn't have a Wikipedia page that goes with it about its history.
I would say it does in a way, and it is fascinating to look at. So you've just got the object.